My name is Kevin Noon. I'm a professor at the Department of Applied Environmental Science at Stockholm University. And for the next 7 minutes or so, we'll be talking about ocean acidification. What I'd like to do is touch on three things. First, the chemistry of ocean acidification, the consequences of ocean acidification, and some of the connections, not just in the planetary boundaries framework, but outside that as well. So let's start off with chemistry. The first slide here shows the carbon dioxide budget globally, and it comes from the Global Carbon Project based in Australia. And towards the left, you can see the amount of carbon dioxide emitted by human activities like fossil fuel burning or cement production. That's the arrow going, the big arrow going upwards. There's another upward going arrow, and that comes from the carbon dioxide emitted from land use change. Of all of the carbon dioxide we emit to the atmosphere, about half of it stays there. And that's why carbon dioxide concentrations are increasing. But what happens to the other half? Well, about 25% or so goes into terrestrial ecosystems. That's the downward going arrow to the trees. And the other 25% ends up going into the oceans. So what happens when you dissolve carbon dioxide in the oceans? Well, the carbon dioxide forms a compound with water called carbonic acid, which then dissociates. That means it splits up and forms two ions, a proton, H+, and a bicarbonate ion, HCO3-. That can dissociate again, giving off another proton and a carbonate ion. And each time a proton is added to water, it becomes a little bit more acidic. So, is that a global issue? Well, yes, it is. This particular image shows three different plots of ocean pH as a function of time. The one on the far left is a pre-industrial case, and the color coding is proportional to the ocean pH. So you can see that the red colors are about 8.2, green colors are 8, the purplish blue colors are 7.8, 7.9. And you can see in the pre-industrial case, most of the oceans were 8 or above in terms of pH. Present day, it's still around 8, but there are fewer areas which are above that. Predicted for the end of the century, you can't see any places at all with pH of 8. Now that doesn't sound like much, right? But keep in mind that a tenth, the 0.1 pH unit, is about a 26% increase in acidity of the oceans. So we're talking about a lot. What are some of the consequences of ocean acidification? Well, this plot shows a lot of different kinds of marine organisms, and it's not so important. You can take a pause and look at more detail. But what you want to concentrate on first is increasing ocean acidity is going to the left in these plots, and calcification rate, that's how rapidly organisms in the oceans turn carbonate into a shell, is on the vertical axis going up. And most of those plots either have a little bit of an inverse U shape or it's just going down, which means that most organisms in the oceans don't like it when it becomes more acidic. They slow down the rate at which they make a hard shell out of the carbonate in the oceans. What does that mean, really? Well, if you're a coral reef, you're under stress from ocean acidification and other things like ocean warming and different kinds of pollutants. And you can go from the kind of beautiful, vibrant, very biodiverse reef you see on the right to the kind of bleached reef you see on the left as a result of those changes in the ocean, including ocean acidification. What are the implications and how rapidly can this happen? Well, the graph on the top shows predicted increases in carbon dioxide concentration for the atmosphere under a number of different scenarios into the future. The bottom shows the aragonite saturation. That's the point at which the equilibrium shifts from making aragonite, a kind of calcium carbonate, a soluble or an insoluble compound in the ocean. And that, you can see, will happen by the early mid-century for the Southern Ocean under most all of these scenarios into the future. So the point at which aragonite becomes soluble or coral reefs might have a very, very difficult time existing at all will be about mid-century or so, not too long from now. Now, that's not the only stressor that marine organisms are facing. It's one of the more important ones, but if you look at some of the other ones like ocean warming and other kinds of pollution, you can see that the oceans are facing multiple stressors. And in particular on this plot, if you looked at the hatched areas, much of the Southern Ocean and much of the North Pacific and Atlantic Oceans we'll be faced by a number of stressors, including ocean acidification. And all of the organisms that live there will be in a much more stressed environment. You can get more detail about this and other issues as well in a book, Managing Ocean Environments in a Changing Climate, that tries to put all of these different stressors together and tells you how they fit with each other, which moves us into the connections part of the presentation. So you've seen this picture before, or at least some version of the picture. This is the image of planetary boundaries. And it's no chance, it's not by chance that ocean acidification and climate boundaries are right next to each other, because the driver for both is the same: how much carbon dioxide we emit to the atmosphere. And just as one example of how this is connected, not only within the planetary boundaries framework, but outside of it as well. So this next to the last slide shows some of the connections between planetary boundaries, ocean acidification, and a couple of other things like food production. So you can see on the top, we can produce food from terrestrial sources, or on the bottom, we can produce food from marine sources. And the things that connect them are our planetary boundaries. So you can see chemical pollution, for instance, from production of food on land might negatively influence coastal areas where we farm or fish for food. Nitrogen and phosphorus cycling, and what we've been talking about so far in terms of ocean acidification, the amount of carbon dioxide that we emit into the atmosphere. And the important thing with this slide is to realize that all of these processes are fundamentally connected with each other. You can't really pull one apart and look at it all by itself. Having said that, though, we'll like to do a little bit of a reminder of what the ocean acidification boundary actually is. It's written in terms of aragonite saturation. That is, it's a chemical equilibrium. And this might be a poster child for planetary boundaries in the fact that that's a very, very easy boundary to define, because it is a chemical equilibrium. If you add a little bit more carbon dioxide to the oceans, aragonite becomes saturated or unsaturated. So this is probably the easiest to define of all the planetary boundaries, and you can see on the slide exactly what it is. Thank you very much.